Alright, let's go. Number 10. The interior of a neutron star. Charles Horowitz at Indiana University was not trying to discover a new state of matter. He was working on a maintenance problem, figuring out how quickly the crust of a neutron star cools after it swallows material from a companion, because the observed cooling curves were not matching the models. Routine thermal conductivity work. He ran molecular dynamic simulations of nuclear matter under compression. Standard nuclear physics says matter has a saturation density. Atomic nuclei sit at about 2.7 times 10 to the 14th grams per cubic centimeter, and they hold that number stubbornly, which is why nuclei do not merge when you push them together. Squeeze harder and the strong force pushes back. Every equation of state used in nuclear engineering assumes this is the regime that matters. The core of a neutron star is 4 to 10 times denser than that. Horowitz and his collaborators, publishing in Physical Review Letters in 2015, found that at densities just below the core, the nuclei stop being nuclei. They stretch into rods. Then sheets. Then sheets with holes. The simulation produced structures the group named nuclear pasta, gnocchi, spaghetti, lasagna, and the point is not the naming. The point is that these shapes have a shear modulus, an electrical resistivity, and a thermal conductivity that no laboratory experiment on Earth has ever measured or can measure. And that is only the crust. The core is worse. Hyperons should appear at those densities, but hyperons soften the equation of state so much that the star should collapse below 2 solar masses, and nicer measured PSR, J740 plus 6620 at 2.08 solar masses in 2021. Free quark matter has been proposed and cannot be confirmed. Kaon condensates were proposed and produced the same collapse problem. Gravitational wave data from GW170817 narrowed the tidal deformability and eliminated the stiffest models, and still did not tell anyone what the substance is. A teaspoon of the stuff weighs about 1 billion tons. It is made of the same neutrons you are made of, arranged in a way physics cannot name. The failure gets sharper when you stop asking what matter is, and start asking how small a question is allowed to be. Number 9. The Planck Scale. Max Planck in 1899 was not looking for a limit on knowledge. He was doing something closer to bookkeeping. He wanted a system of units that did not depend on the length of a French metal bar or the mass of a particular cylinder. Units any civilization anywhere would derive independently. He combined the gravitational constant, the speed of light, and his own new constant, and read off what came out. Ordinary optics is straightforward. To resolve something small, you need a wavelength shorter than the thing. Shorter wavelength means higher photon energy. There is no theoretical ceiling on photon energy, so there should be no theoretical floor on resolution. This is the assumption every accelerator on Earth is built on. Combine that with general relativity, and the assumption dies. The number that falls out of Planck's combination is 1.616 times 10 to the minus 35 meters. A photon with a wavelength that short carries about 1. 22 times 10 to the 19th giga-electron volts of energy. Compute the Schwarzschild radius of that much energy, and it is larger than the wavelength itself. The probe collapses into a black hole before it can report. David Gross and Paul Mende showed in Nuclear Physics B in 1988 that string scattering at those energies produces the same wall from a completely different direction. Every escape route has been tried. String theory's T-duality builds in a minimum length rather than removing it. Loop quantum gravity in the 1995 Rovelli and Smolin area spectrum makes space discrete, which forbids the question rather than answering it. Asymptotic safety keeps gravity finite but does not restore resolution. Doubly special relativity predicted that high-energy photons would arrive late across cosmological distances, and the Fermi telescope's observation of gamma ray, burst 090510 in 2009, found no delay at all. Not a funding problem, not an engineering problem. There is no possible instrument in any century that can look beneath it. If the smallest scale is closed to us, the emptiest one should at least be simple. Number 8, the vacuum. Wolfgang Pauli reportedly did this calculation as an idle exercise between more serious problems. Quantum field theory says every field has a ground state that still fluctuates, the zero-point energy. Pauli added up the contributions for the electromagnetic field, applied a reasonable cutoff, and worked out what that energy would do to spacetime through general relativity. He found the resulting universe would not reach the moon. Empty space, in the standard picture, should have an energy density. That is not controversial. The Casimir effect measures a consequence of it, and Lamb shift measurements confirm the underlying fluctuations to 10 significant figures. General relativity then says any energy density curves spacetime. Combine the two and you can predict how fast the universe should expand. The prediction misses by 120 orders of magnitude. Steven Weinberg laid it out in Reviews of Modern Physics in 1989 in a paper simply titled The Cosmological Constant Problem. Cut the field theory off at the Planck scale, and you get a vacuum energy density around 10 to the 113th joules per cubic meter. The observed value from supernova and CMB data sits near 10 to the minus 9th. That is a factor of 10 followed by 120 zeros. It is the largest disagreement between prediction and measurement in the history of quantitative science. Supersymmetry was the great hope. Bosonic and fermionic contributions cancel exactly. But they only cancel exactly if supersymmetry is unbroken. And it is visibly broken, and breaking it at the TV scale still leaves you 60 orders of magnitude wrong. The LHC has found no superpartners. Quintessence replaces the constant with a field and inherits the same fine-tuning. Unimodular gravity decouples the vacuum energy from gravity, but cannot say what sets the leftover. Weinberg's own 1987 anthropic argument in Physical Review Letters predicted roughly the right value by assuming galaxies had to form, and most physicists regard that as surrender. Physics calculated the energy of nothing, and got it wrong by more than it has ever gotten anything right. The vacuum at least gives a wrong answer. There are places that give infinitely many. Number 7. The Cauchy Horizon. Roy Kerr was not investigating the interiors of black holes. In 1963, he was doing classification work, searching for exact solutions to Einstein's field equations with a particular algebraic property, the kind of technical exercise that fills a mathematical physics career. He found one, published it in Physical Review Letters in a paper barely a page and a half long. And it turned out to describe every rotating black hole in the universe. General relativity is deterministic in a very precise sense. Specify the fields on a space-like surface, and the equations propagate that data forward uniquely. One past, one future. This property, the Cauchy development, is what makes the theory physics rather than description. Inside Kerr's solution, there is a surface where that development simply ends. Beyond the inner horizon, at a radius determined by the mass and spin, the equations admit infinitely many continuations, all equally valid, all consistent with identical initial conditions. Roger Penrose recognized the problem in 1968 and responded with the strong cosmic censorship conjecture: nature must prevent observers from ever reaching such a surface. It was a conjecture, not a theorem, and it has been under attack ever since. Eric Poisson and Werner Israel proposed mass inflation in Physical Review D in 1990. Infalling radiation blue shifts without bound and generates a curvature singularity that seals the horizon. It works, but the singularity is weak. Tidal forces integrate to a finite deformation, so an observer crosses it intact. Mihalis Daframos and Jonathan Luke proved in 2017 that a continuous extension of the metric exists, killing the strongest form of the conjecture. Cardoso, Costa, Destunis, Hintz, and Janssen showed in Physical Review Letters in 2018 that near-extremal charged black holes in a universe with dark energy violated outright. Hollins, Wald and Zahn argued in 2020 that quantum effects restore censorship by requiring a theory of quantum gravity nobody has. Determinism is not a law of physics. It is a boundary condition, and there are surfaces inside real astrophysical objects where it does not hold. Determinism fails at one edge of the universe's history. At the other edge, everything fails. Number 6. T equals 0. Stephen Hawking's doctoral work was not about the origin of the universe. He was extending a technique Penrose had developed for gravitational collapse, a topological argument about trapped surfaces, and he noticed the argument could be run in reverse. Point it backwards in time at an expanding cosmology, and it produces the same conclusion. The Hawking-Penrose theorems, finalized in the Proceedings of the Royal Society A in 1970, showed the initial singularity is not an artifact of assuming perfect symmetry. It is generic. Below the Planck time, 5,039 times 10 to the minus 44th seconds, both general relativity and quantum field theory make claims about the same region. Relativity says spacetime is a smooth manifold with definite curvature. Quantum mechanics says any quantity confined to that scale has uncertainty exceeding its own value. The manifold cannot be defined, and the equations that live on it cannot be written. Attempts to quantize gravity directly fail at second order. Goroff and Sagnati demonstrated in Nuclear Physics B in 1986 that pure gravity produces a two-loop divergence that cannot be absorbed by any redefinition of the theory's parameters. The theory is non-renormalizable, not difficult, not incomplete. Ill-defined. Inflation was expected to erase the problem and did not. Bored. Guth and Vilenkin proved in Physical Review Letters in 2003 that any spacetime with average expansion greater than 0 is geodesically incomplete toward the past, inflating or not. Hartle and Hawking's no-boundary proposal replaces the singularity with a smooth rounding in imaginary time, and disagrees with the Vilenkin tunneling proposal about which universes are probable. Loop quantum cosmology, in the Ashtekar, Pawlowski, and Singh bounce of 2006, replaces the singularity with a rebound from a prior contracting phase, and cannot say what preceded that. String gas cosmology moves the problem into a regime with no observational access. Everything you are made of has a history. That history begins at the one instant for which no physics exists. The early universe is unreachable. The next item reached us anyway. Number 5. Above the GZK Cutoff. Kenneth Greisen at Cornell and independently Georgy Zatsepin and Vadim Kuzmin in Moscow were doing consequence chasing. The cosmic microwave background had been announced in 1965. Within a year they asked the obvious follow-up question if space is full of low-energy photons. What happens to a very fast proton traveling through it? A proton above roughly 5 times 10 to the 19th electron volts sees those cold photons Doppler shifted into the gamma range. It collides with them, produces pions, and bleeds energy. The effect compounds. After about 50 to 100 megaparsecs, whatever the proton's original energy, it is dragged down below the threshold. This is not a soft limit. It is a hard ceiling on any particle that has crossed intergalactic distances. On the 15th of October 1991, the Fly's Eye detector in Utah recorded a particle at 3.2 times 10 to the 20th electron volts. That is 6 times over the ceiling, about 51 joules carried by a single subatomic particle, comparable to a baseball thrown at 90-odd kilometers an hour. Bird and colleagues published it in the Astrophysical Journal in 1995. It was dismissed as a detector fluke until they kept arriving. The telescope array recorded the Amaterasu particle on the 27th of May 2021 at 2.44 times 10 to the 20th electron volts, published in Science in November 2023. The explanations have been picked off one by one. A nearby source would work, except Amaterasu's arrival direction traces back to the local void, where there is nothing. Heavy nuclei rather than protons would raise the threshold, except the Auger composition data does not support a pure heavy flux at the top energies. Magnetic deflection was invoked, except the deflection required exceeds any plausible intergalactic field. Lorentz invariance violation would dissolve the cutoff entirely, and would also break the tests that constrain it to 1 part in 10 to the 20th. Something within 100 megaparsecs, cosmically, the same neighborhood is doing this. Nothing there is visible. The next entry is on this list for the opposite reason. Number 4. The muon's magnetic moment. The muon G2 experiment was never designed to overturn anything. It is a precision audit. Julian Schwinger calculated the first correction to a lepton's magnetic moment in 1948, and the quantity has been the standard model showcase ever since. Electron G2 agrees with theory to 12 decimal places. The muon is 207 times heavier, which makes it 40,000 times more sensitive to heavy virtual particles. If anything unknown exists, the muon should feel it first. The prediction and the measurement should match. For decades, they did not. Brookhaven's E821 experiment closed in 2001 with a discrepancy of roughly 2.5 standard deviations. The storage ring was floated on barges and trucked 3,200 miles to Fermilab. The first result came in 2021 at 165,919,2040 times 10 to the minus 11. The 2023 result tightened it. And by 2025, the experimental uncertainty was down to about 127 parts per billion, the combined tension reaching 5 standard deviations against the accepted theory number. Here is where this entry diverges from every other one on this list. The theory number was wrong. The dominant uncertainty was never in the experiment. It was in hadronic vacuum polarization, a quantity that cannot be calculated perturbatively and was historically extracted from electron-positron collision data. In 2020, the BMW collaboration published a lattice QCD calculation in Nature that landed much closer to the measurement. In 2023, the CMD3 experiment in Novosibirsk remeasured the pion production cross-section and disagreed with every previous measurement of it. By 2025, the Muon G2 theory initiative had shifted its consensus prediction toward the lattice result, and the anomaly largely dissolved. Supersymmetric explanations were written, leptoquark models were written. Hundreds of papers proposed new particles for a gap that turned out to be a bookkeeping error in the hardest part of the calculation. This is what physics is breaking usually means, which is exactly why the entries that survive that filter deserve attention. The muon was a false alarm. The next one is inside your own body. Number 3, the interior of the proton. Friedman, Kendall, and Taylor at SLAC in 1968 were doing form factor measurements, bouncing electrons off protons to map out how the charge was distributed. Everyone expected a soft, diffuse blob. The scattering pattern would fall off smoothly. It was meant to be a confirmation run. Mass in every framework before that is additive. A water molecule weighs what its atoms weigh. An atom weighs roughly what its nucleons weigh. The proton is made of 3 valence quarks, 2 up, 1 down, so the proton should weigh what they weigh. An up quark is about 2.2 mega electron volts. A down quark is about 4.7. The proton is 938.272. The quarks account for around 1%. The QCD collaboration, led by Yibo Yang, published a lattice decomposition in Physical Review Letters in 2018, roughly 9% from the quark condensate, about 32% from quark kinetic and potential energy, about 36% from the gluon field, and the remaining quarter from the trace anomaly, a purely quantum effect with no classical counterpart at all. 99% of your mass is binding energy in a field. Nobody can solve the equations that describe it. Quantum chromodynamics is asymptotically free, which means the coupling constant grows as energy drops, which means at the energy scale of an actual proton, the perturbation series diverges instead of converging. Every calculation above is numerical, supercomputers evaluating a discretized approximation on a finite lattice. Confinement itself has never been proven. The Yang-Mills existence and mass gap problem is one of the 7 Millennium Prize problems and remains open. And the proton radius measured with muonic hydrogen by Pohl's group in Nature in 2010 came out 4% smaller than the electron-based value, at 7 standard deviations, which took a decade to argue down. The theory of what you are made of has no closed-form solution. If matter is unsolvable, at least observation should be well defined. Number 2. Wherever a measurement happens. John von Neumann was doing housekeeping. In 1932, he set out to give quantum mechanics a rigorous mathematical foundation in Hilbert space, to clean up the physicists' informal manipulations into proper axioms. In doing it, he found he could not describe the theory with one process. He needed 2, and he numbered them. Process 2 is the Schrödinger equation. It is linear, deterministic, reversible, and continuous. Given a state now, it gives the state at any later time, exactly. Every prediction quantum mechanics has ever made correctly comes from it. Process 1 is measurement. It is nonlinear, indeterministic, irreversible, and discontinuous. It has no equation. There is no formula for when it triggers, no timescale for how long it takes. No threshold of size or mass or complexity that switches it on. Max Born supplied the probability rule in 1926 in a footnote added in proof. Gherardi, Rimini, and Weber tried to make collapse physical in Physical Review D in 1986 by postulating spontaneous localization at about 10 to the minus 16th per particle per second, a genuine, testable modification. Donati and colleagues ruled out the gravitationally induced version in Nature Physics in 2021 by looking for the X-rays it should emit. Meanwhile, Fine and colleagues demonstrated interference for molecules of 25,000 atomic mass units in 2019, and no deviation from linearity has ever been observed at any scale. Copenhagen defines the problem out of existence by declaring the apparatus classical. Many worlds keeps the linearity and cannot derive the Born probabilities in a way its own advocates agree on. De Broglie, Bohm restores determinism at the cost of explicit non-locality. Cubism makes the state a description of belief. Decoherence explains why interference becomes unobservable and why the pointer basis is selected, and as Adler and Kent have both argued in print. Does not explain why one outcome occurs rather than another. The most precisely confirmed theory in the history of science contains a step written in English. Which brings us to the place where the equations stop returning numbers at all. Number 1. The singularity. Carl Schwarzschild solved Einstein's field equations from a trench on the Russian front in 1916. He was serving in the German artillery, calculating shell trajectories, and he worked out the exact geometry around a spherical mass in his spare time and mailed it to Einstein, who had not believed an exact solution existed. Schwarzschild was dead within 4 months. His solution has 2 special radii. One is the event horizon, which turned out to be a coordinate artifact. Nothing physical happens there. The other is the center. At the center, the Kretschmann scalar, a coordinate-independent measure of curvature, goes to infinity. That is not a mapping problem. Density, tidal force, and space-time curvature all return values that are not numbers. For 50 years, this was assumed to be an artifact of assuming perfect spherical symmetry, which nothing in nature has. Roger Penrose ended that assumption in Physical Review letters in 1965 with a 3-page proof. Once a trapped surface forms, geodesic incompleteness follows regardless of symmetry, regardless of the details of the collapsing matter. Real stars produce real singularities. He received the Nobel Prize for it 5 years later. Cosmic censorship was proposed to contain them and has never been proven. Leaner and Pretorius found black string configurations that violate it in 2010. Crisford and Santos found violations in anti-de Sitter space in Physical Review letters in 2017. Fuzzballs replace the interior with a string-theoretic microstate geometry and cannot be observed. Planck stars and gravastars postulate a quantum gravitational core and cannot be tested. Every proposed resolution requires the theory of quantum gravity that item 6 established does not exist. And here is the part that gets left out. The Milky Way is estimated to contain on the order of 100 million stellar mass black holes, plus Sagittarius A at 4. 3 million solar masses, imaged by the Event Horizon Telescope in 2022. LIGO and Virgo have now cataloged more than 200 mergers. This is not a rare pathology at the edge of the cosmos. There are more places in this galaxy where physics returns no answer than there are stars visible from Earth on the clearest night. Look at what these 10 places have in common. Not one of them sits at the frontier. Neutron stars are the ordinary corpses of ordinary stars. Protons make up your hands. Measurement happens every time a photon hits your retina. Singularities are as common in this galaxy as villages are on a continent. Every breakdown on this list lives at the dead center of our most tested, most confirmed, most relied upon theories. The universe is not confused about what it is doing. It has never once hesitated. We are the ones holding an incomplete description and calling the gaps anomalies. If you want to see more videos like this, click the video on screen now.